Okay, let's get back to what I discussed previously. Remember the Carnot cycle? Yesterday we discussed about Carnot cycle. It is impossible to implement Carnot cycle directly to the real engine. Why? This one is related with entropy definition. Entropy is a state function, similar like internal energy, and then Gibbs free energy, enthalpy, and so on. So this entropy, the delta S of entropy, it's not depend on thermodynamic pathway, but it's only depend on the initial and final state. Remember when we have a several pathway, as long as both of these two conditions that we want to check, the entropy will remain the same. Can be used for the upper pathway, A pathway, or B pathway. Okay. Now, by definition, entropy is QR by temperature. R means reversible. So, because entropy is not depend on the course of the process, it's only depend on the initial and final state. Okay, initial and final state. So we can assume that delta S irreversible is equal to delta S reversible, and it's equal to integral dou Q reversible by temperature. And please be aware that delta S irreversible, it's not the same as the Q irreversible divided by temperature. We will have an example related with this one. The one that you calculate based on thermodynamic calculation is reversible heat, not irreversible heat. The irreversible heat should be measured. You need to have a device that measure the heat coming out from the system or consumed by the system, not calculated. Okay. This one is just to emphasize the entropy as a state function. And remember, as long as it's cycle, this is an example, delta S 1, 2, 3, 4, and return to 1. So the delta S should be equal to 0. The other one that's also important is, let's say there is a two system with different temperature. One is T1, the other one is T2, like this. Okay, the state is T1 higher than T2. The temperature of the system on the left, the first system, is higher than the temperature on the right. So what happened now with entropy? Because the temperature of system 1 is higher, heat will transfer from the left to the right, minus Q. If we check from system 1 point of view. In the opposite way, if we check from the system number 2, it means the heat absorbed by the system number 2. So instead of putting minus Q, if we check from number 2, it will be positive. So please be aware about this. When we consider as system number 1, heat release, the temperature decrease. On the opposite way, we check from the system number 2, the absorbed heat, temperature increase. Now, which temperature that we should use? We have to use the temperature of the system accordingly. So for system 1, use T1, while for system 2, use T2. So in total, delta S total should be equal to delta S1 plus delta S system 2, which would be equal to minus Q by T1 plus Q by T2. It's not equal to 0. Okay? So delta S total would be like this. Up to this point, any question? It's simple, right? With this principle of entropy. Now, why we have to understand the entropy? This is the main reason. Remember, by definition, delta S is equal to Q reversible by temperature. Okay? And remember that the delta S irreversible is equal to delta S reversible is equal to Q reversible divided by temperature. Okay? Why we have to understand this? What we calculate based on thermodynamics is always reversible heat. Okay? When you have non-reversible process, you need to measure the amount of heat. In other words, for non-reversible process, you need to measure the irreversible heat. But please be aware that entropy of irreversible is not related with heat irreversible. Okay, this one just to distinguish which one is based on calculation, which one is based on measurement, the real one. Okay, now let's see when we put the entropy change into the ideal gas system that we used to work with. The first one is isothermal process. Delta U is equal to 0. You remember about this, right? Because isothermal means delta T is equal to 0. While delta U itself is mCV, constant volume multiplied by delta T. If delta T is equal to 0, delta U would be equal to 0. That one is simple. How about the Q itself? Q should be equal to minus W. And then we can calculate that one. So because we know that Q is equal to integral nRT divided by volume dV, delta S would be Q by T. So you will have two temperature here. You can cancel out both temperature. So the result would be delta S equal to nR ln V2 by V1. Or we can replace volume by P1 by P2. Okay, please remember for isotherm, P1 V1 is equal to P2 V2. So when you have V2 by V1, it means it should be equal to P1 by P2. Similarly, for isobaric process. Isobaric means delta P is constant. Delta P is equal to 0. Pressure is constant. So Q would be equal to delta H. This is the result. Don't forget, delta S is Q divided by temperature. So this is the formula for entropy. And remember, we're also discussing Cp can be constant if we assume at a certain range, but Cp can be a function of temperature when the increase of temperature is relatively high. And this is the example. How about for isometric process? Isometrics mean delta V is equal to 0. So the Q would be equal to NCV, constant volume. Take a note, in isometric, you have to use CV, while in isobaric, you have to use CP, constant pressure. So entropy in isobaric is not the same as entropy in isometric. The difference is coming from the heat capacity. One in constant volume, the other one is in constant pressure. Similar like CP, CV can have two different approach. The first one we can consider CV is constant. The second one we can consider CV as a function of temperature. When the increase or when the temperature difference is relatively high, you have to use CV as a function of temperature. And the last one is adiabatic. This is very simple because for adiabatic, the heat should be equal to 0. If the heat equal to 0, for sure entropy will be equal to 0. Because of this is the condition when we consider as isentropic condition. Isentropic condition. When you have initial entropy is equal to the final entropy. So delta S12 is equal to 0. Okay, so adiabatic reversible sometimes consider the isentropy is equal to adiabatic reversible. Why we have to use reversible things here? Because by definition, remember, the entropy is equal to heat reversible divided by temperature. Is it possible to have adiabatic non-reversible? Yes. When they consider the process is adiabatic, but the measurement show there is a heat consumed or heat release. It should be very small. Okay, so in that case, it's not really isentropic process. And where is this isentropic condition occur? Remember the last diagram that Pasanggono mentioned? When we have pH diagram, there is a dome forming like this. And then Pasanggono also explained this is the isothermal curve. And he also explained that there is a curve with this direction. There is S1, S2, and S3. So along this curve, the entropy will remain the same. That's why we consider this as isentropic process. Will it be important? Yes. We will use isentropic condition as ideal condition for later on. Compressor, turbine, pump, we will consider that one as isentropic condition for the ideal case. In addition, there is also a similar things like isentropic. We consider this as isentropic when the delta H is equal to 0. We call this as isentropic condition. Okay, sorry, isentropic condition. No. Entropy condition, TH. Sorry. Entropy condition. This is when H1 is equal to H2. So like I mentioned previously, isentropic normally occurred in compressor, turbine, expander, and so on. While isentropic condition, this one occurred in JT valve. JT stands for Joule Thomson. Okay, we will learn about this in details later when we discuss about heat pump. Okay, so now at least you know the basic idea about entropy changes. Up to this point, any question? What the definition of entropy, how to calculate entropy for each thermodynamic process. So at least you know the principle of this, right? Okay, I think I will give the opportunity to Pak Sanggono to explain about the real gas. Or if Pak Sanggono have additional comment regarding with entropy, please, Pak.
Okay. So right now we learned about the entropy in the textbook. It is in the chapter 5, second law, and then later we will go back to chapter 3. It is about the ideal gas and real gas calculations. So basically we will not follow from chapter to chapter like in the textbook, but sometimes we have to jump to chapter 5 and then back to chapter 3 and then jump again, things like that. Okay, that's my additional comment.
Yeah, thank you very much, Pak. Because the idea is to make you easier to understand. So you know, first law of thermodynamics, second law of thermodynamics, what is the important definition like internal energy, enthalpy, entropy, and so on. And then you can understand the reason why there is an equation that make it easier to understand for real gas. So Pak Sanggono will explain about the real gas, what is the difference between ideal gas, and how to calculate with relatively simple equation. But later on, we will use a software to make the calculation much easier. Okay, please, Pak Sanggono.
Okay, yeah. So we are in chapter 3. In the Smith, Van Ness, Abbot we heard, chapter 3 is about the volumetric properties of the pure fluids. Earlier today we had the second law of thermodynamics. Okay, so we are coming back to chapter 3. It is about the volumetric properties. Or to be specific, it is about the cubic equation of state. Later in the afternoon, you will have a test about how to calculate volume, compressibility from the cubic equation of state. Okay, but the idea is this actually. You are familiar with the concept of the ideal gas, that is PV equal nRT. PV equal RT, with N equals to 1 mole. Now, for the real gas, there is a correction factor. That is the coefficient of B over here, and then the term A over V square. So basically, it is just a correction factor. The basic equation for the gas is the ideal gas. Later, the definition of the ideal gas, we will go through that, okay? But let's assume ideal gas means it is gas. PV over RT, PV equal nRT. PV equal RT, PV equal nRT. Now, there is a beginning of the correction. It was done by van der Waals back in the 1873. He put the correction for this term. What is the unit over here? It should be the same as the unit of the pressure. If the pressure unit is bar, then this is bar. What is the unit of A? Well, we will check later. If the volume is cubic centimeter per moles, there is a squared over here, then we will know the dimension, the unit of the A. Okay, the same thing like B. What is the unit of the B? Since we have volume, then the unit of the B is the same as the volume, cubic centimeter per mole. Okay, this is the van der Waals equation of state. Remember, in the thermodynamics, all we can measure is just pressure, volume, and temperature, PVT. From that known or measured variables, then we will calculate internal energy, enthalpy, and then later entropy. And you are familiar with isentropic process, isenthalpic process for the delta H0. And then there is a constant temperature, isotherm. Constant volume, it is isochor, isometric. Constant pressure, it is isobar. Okay. Now, there is a further modification after van der Waals. The basic principle is the same. It is just to add correction factors. Not in the first term, but it is added on the second term. The V volume, it is squared of the V over here, it is squared, but they put another B over here. And then there is A bracket of the T, it is not A multiplied by T, it is A as a function of T, of temperature. Okay. Then there is a generic equation of state that can be valid for any modification. We have the term RT over V minus B, and then over here there is another parameter, that is epsilon, there is sigma, there is A as a function of T. And then let's check. It is just a mathematic, it is a simple mathematic. The definition of the Z, that is compressibility factor, it is PV over RT. PV over RT. If I have over here V, in order to make it into Z, what do we have to do? We multiply with V over RT. Okay? Multiply by V over RT, we get Z over here. Multiply by V over RT, what do we get over here? Well, the RT will cancel out, and then we have V over V minus B. And the same thing, we multiply this with V over RT. Finally, we get in the form of the Z over here. It is identical, actually, this and this. The difference is just that Z is PV over RT. Okay, it is equation 48. Or in another form, it can be written as this. Okay, that is part of the mathematical manipulation. All we need to do is we use that equation. Okay, so this is Z equal PV over RT. If it is ideal gas, volume equals Z multiplied by the volume of the ideal gas. Okay, Z equals 1 if it is ideal gas, because PV over RT equals 1 in the ideal gas. Now, in order to use that equation, we need to understand the parameter over here. Okay, this is the list of the equation of state. So it is like ideal gas, but it is for the real gas. We use van der Waals in the beginning. It is updated by Redlich and Kwong, and then it is updated later by Suave, Redlich Kwong, and then now it is Ping Robinson, and there are many others actually, hundreds. Up to now, I think there are 200 or 300 equation of state. The basic principle is the same, but there is some parameters over here that we need to understand. Okay, first, alpha. Alpha as a function of temperature. TR is the reduced temperature. What is reduced temperature? That is temperature divided by critical temperature. That is what we call reduced temperature. So if there is alpha and then bracket TR, it is not the multiplication of alpha with TR, but it is alpha as a function of TR. If we have alpha for SRK as a function of TR and omega. What is that omega? Later we will check in the table. Omega is the eccentric factor. Okay, for round molecule like methane, CH4, omega is very low, but for long chain molecule, that omega is higher. This is a function of TR and omega. Where is omega? It is here, omega. There is omega over here. Where is the TR? The TR is over here. So the alpha for the SRK is a function of this. This is SRK. Now let's understand alpha of the Ping Robinson. This is as a function of TR and omega, the same thing. We have omega here, we have omega, and we have TR, but with different coefficients over here. Okay, so over here we have alpha SRK, we have alpha Ping Robinson. How about if we use van der Waals? That alpha as a function of TR equals 1. How about if we use Redlich Kwong? That alpha as a function of TR is just TR to the power of minus half. Okay, this is how to get alpha TR. Why do we need that alpha TR? Because we need later in the calculation of the sigma, omega, etc. Okay, so there is a definition of the sigma of the equation of state. There is epsilon. This is a capital omega. The small omega is this. The capital omega is this. There is a psi over here, and there is a critical compressibility at the critical point. Okay, so by knowing these parameters, we will be able to use this equation. What is the purpose to work on this equation? Basically, it is PVT. When we get the data of the pressure and we know the temperature, then we will be able to calculate the volume. Okay, later we will go through the example so that it is clear for you. Okay. Okay, before I go to the example, this is the equation. There is another equation of state that is what we call virial equation of state. I think I will go briefly. It is from the example 3.8. Virial equation of state is explained in the equation 336 and equation 338. Okay, I think we will go to this virial later. We will concentrate first into the equation of state that is in the table over here. Okay. Now, it is easier to understand once we work with the example. We have normal butane over here. The pressure is 9.4 bars. The temperature is 350 Kelvin. So remember PVT, we know the temperature, we know the pressure. The one that we don't know is volume. Therefore, the question is find the molar volume, volume per mole, with the two principles, one in the saturated vapor and the other one saturated liquid, using Redlich-Kwong equation of state. Okay, now in order to calculate, we need to get the TR and PR. Remember what is TR? TR is the temperature divided by the critical temperature. What is the temperature? Is 350. How to find the critical temperature? How to find the critical pressure? Okay, later we will go through the table, but the critical, the reduced pressure is the actual pressure divided by the critical pressure. What is the actual pressure? 9.4. The critical pressure is 37.9. Then we get this reduced pressure. Okay, let's go to Appendix B in order to understand, in order to check the critical temperature and pressure. How to check? You go to an Appendix B. So over here, there is an Appendix B. What is the page of the Appendix B? It is page 650. So you type over here 650, enter, then you are at the Appendix B. And then there is a table in the Appendix B. Let me make it bigger. Okay. It was normal butane. This is molar mass of the normal butane. Normal butane is C4H10. What is the molecular weight of the normal butane? Carbon is 12 multiplied by 4 is 48. C4H10. The 10 hydrogen is 10, so 48 plus 10, it is 58. This is the molecular weight of the normal butane. The omega is the eccentric factor. It is 0.2. The critical temperature in Kelvin, this is 425. The critical pressure in bar, it is 37.96. The other column is critical compressibility. This is critical volume. This is the unit. And there is another one is the N in Kelvin. We just concentrate on this omega, critical temperature, critical pressure. Okay, the unit is over here. What is the unit of omega? It is dimensionless. Okay, up to this point, are there any questions on how to read the properties of pure species? Please ask if you have problems with this. Okay, if there is no question, I go back to this. The TR, this is critical temperature. The PR, this is critical pressure. You get the TR is 0.8. The PR is 0.25 approximately. Now, we have to calculate the parameter Q. The Q is given by equation 3.51. Okay, let's check that equation 3.51 so that you know where it comes from. Okay, 3.51 approximately is on page 95. Okay, let's type 95. 3.51 Okay, this is the equation 3.51. Let me make it bigger. Okay, this is equation 51. In order to calculate beta and Q, we need to get omega. This is the capital omega. And we need to have psi, we need to have alpha as a function of TR and omega. We need to have omega capital, we need to have TR over here. Okay, beta and Q. Now we go back over here to calculate Q and beta. This is the equation psi multiplied by TR divided by omega TR. How do we get this? What is the omega? What is the psi? What is the omega? If we use Redlich-Kwong equation of state, since it has been determined that we use Redlich-Kwong, then we check that omega, psi, and omega. Let's check in the column over here. This is Redlich-Kwong. This is psi. This is omega. Okay, let's check the psi first. What is in Redlich-Kwong? It is 0.4 something. What is the omega? It is 0.08. Okay, now we go back over here. This is psi. This is 0.4. This is omega. This is 0.08. So you just put over there, and then the TR is the TR that we just calculated, 0.82. We put over here, and then we get Q over here, 6.6. How about beta? This is beta. The equation is omega PR over TR. This is the omega, 0.08. This is the PR, reduced pressure. This is reduced temperature. This is the value of beta. So we get Q and beta. Up to this point, are there any questions? Please ask question if you don't understand. It is simple, actually. Don't worry too much, because you just take a look at the table, then put over here, you get that beta, you get that Q. Okay? Now we use this equation of Z. We have calculated beta. We have calculated Q. You just put that values over here. All you get is just Z. Okay? Now, how to get the root of the Z? First, we need to recognize that this is cubic equation of state. Cubic mathematical equation. When we have Z multiplied by Z, it is quadratic. When we have another Z over here, it is cubic. If we need to find the root of that Z, we will get 3 roots because it is cubic. Okay. Now, over here, when we do substitution, we get that Z 0.83. How about this is Z number 1? How about Z number 2? How about Z number 3? Because there is supposed to be 3 Z's. Sometimes we get that Z equals negative, or that Z is not a real number, but it is imaginary number. In that case, we just take the real number, that is the one below 1.0. Okay, so we get 0.83. Now we need to find the volume of the vapor. This equation is for the vapor, saturated vapor, from equation 48. Okay, later in the B, we will calculate for the saturated liquid, because we have liquid and vapor all together. Okay, this is volume of the vapor, Z RT over P. Z is the one that is calculated. R, later we will check this R. temperature is 350, pressure is 9.4. Okay, you just calculate this, you get that volume of the vapor is 2500 cubic centimeter per mole. Now, how to check this R? We need to get with the proper unit. If our target is volume, then try to find R with the cubic centimeter or with the liter or with cubic meter, things like that. Don't take the R as the joule per mole Kelvin, because you have to transfer that unit into cubic centimeter. In order to do that, check in the appendix. Okay, we have the listing of the appendix over here. This is in the table of contents. What is the page of the appendix? It is on page 648. I will open up 648 over here. 648. Conversion factor and values of the gas constant. Okay, so you get the gas constant over here. This is the gas constant. It is your decision. You can choose which one the most appropriate. Okay, we need to find out if there is a volume. This is cubic centimeter. This is cubic centimeter. The pressure was bar. Okay, we will take this. The value is 83.14. If the pressure is not in bar, if the pressure is in kilopascal, remember 1 atmosphere is around 100 kilopascal, then this is the R. If the pressure is in atmosphere, you select this 82.06. Okay, this is from page 649 in the appendix. Okay, go back to the original. So we get value of the V. This is cubic centimeter per moles. The experimental value that is measured in the laboratory, it is 2482. So it is not far from the calculated value. Up to this point, are there any questions? Okay, I will continue. This is for saturated liquid. Previously it was for saturated vapor, now it is for saturated liquid. Using Redlich-Kwong, the same thing. We put the beta, we put the Q, put everything over here, and then get the root of the Z. You get Z 0.04. The volume of the liquid is CRT over P. This is 133. Okay, let's compare. If it is vapor, 1 mole, the volume is 2500. If it is liquid, the same 1 mole, the volume is much less. That is only 133. So this one is maybe 20 times more than this. Okay, this is volume of vapor, this is volume of liquid. So we have answered the question of the problem. Find the molar volumes of the saturated vapor and saturated liquid using the Redlich-Kwong equation. So later, if you are asked the same question but using Ping-Robinson, what do you have to do? You just use the same thing. The difference is just the value of the omega capital is difference. The value of the psi is difference. Redlich-Kwong is 0.42, Ping-Robinson is 0.46. Okay, then calculate the alpha, things like this. Okay, up to this point, are there questions on how to calculate compressibility factor or the volume? It is simple, actually. Okay, there is no question. I will go to one example of the virial. It is similar. We have isopropanol vapor at 200 Celsius. we need to calculate at 10 bars what is the volume. So PVT, this is the P pressure, this is the T temperature, we need to calculate the V using the ideal gas, using the virial coefficient. Later we will go to this virial coefficient, virial equation. This is the ideal gas, V equal 1, or V ideal, Vig, RT over P. We enter the R, temperature, pressure, then we get the volume, if it is ideal gas calculation. And then when we use the equation 3.36, let me open this. 3.36. Equation of state. This is a virial equation, page 92. I enter over here, page 92. What was the equation number? Let me check back. The equation number 36 and 38. Okay. 36, this is the equation of 36. Let me make it bigger. Z, PV over RT, it is a function of pressure. That is 36. Okay. Now 38, it is similar. 38, Z, PV over RT, this is a function of volume. Okay, so we can make equation as a function of volume or a function of pressure. Then we need to calculate based on the pressure calculation and volume calculation. So this is V equal RT over P plus B. The B value is known, then we get the V over here. The Z, compressibility factor, is PV over RT. That volume is used, 3546 over RT, we get 0.9. That is compressibility based on the pressure function. Now the C is based on the volume function. The B coefficient is known, C coefficient is known, then we need to calculate the V. This is calculated through the iteration. You put the V from the ideal gas and then calculate the V over here. After we get that V, we use that V as the VI over here. Over here, I plus 1 originally, later we have I plus 2. Later we have I plus 3, I plus 4. That is iteration until the value of the V over here is the same as the V over here. Okay, finally we get volume is 3488 cubic centimeter per mole. The Z is this volume divided by the volume in the ideal condition. We get 0.88. Okay, so if we use virial pressure, it is 0.9. If we use virial volume, it is 0.88. Which one is the correct one? The correct one is the one that is measured in the laboratory. That is measured in the pressure, temperature, and volume. Okay, up to this point, are there questions for the virial? This is simple. Okay, if there is no question, this is the last one. We use the generalized correlation. Okay, this is the generalized correlation for Z. Compressibility equals Z, 0, Z, 1, and then multiply by the omega sphericity. It is equation 53. This is an example number 10. We have normal butane. The temperature is 510 Kelvin. The pressure is 25 bar. We need to determine the volume using ideal gas state, using generalized compressibility factor, using another one, that is the B prime and C prime, but we will not go through the C and D, we just go through the A and B, okay, to learn how to use the generalized compressibility factor calculations. Okay, in the ideal gas state, it is simple, V equal RT over P, you put temperature, you put pressure, this is the R, we get the volume as an ideal gas. Now, if we want to use the concept of Z0 and Z1, we will use a chart or table that we call the Pitzer and Lee Kessler. It is on table D1 and D2. Later we will go to that table, but in order to use that table, we need to calculate the TR and PR. Remember TR? Temperature divided by the critical temperature. What is the critical temperature of normal butane? We will find out in the table. This is critical pressure. Then we get the PR 0.65. The PR is 1.20. Now, we find the table D1 and D2. How to find out? Back to the textbook. Over here, there is appendix. Okay, there is a D. The D appendix page is page 663. Okay, we type over here 663. Then we get into appendix D, Lee Kessler, or we call it Pitzer generalized correlation table. There are tables D1 up to 4 up to 16, but what we need to use is just the correlation for the compressibility factor. Later in the semester, we will use the residual enthalpy, the residual entropy. But today we just use D1 up to D4. To be specific, it is just D1 and D2. Okay. This is the table of D1 to get the value of Z0. How to get that? How to read that? We need to get the PR, that is reduced pressure. For instance, if our reduced pressure is 0.6, okay, then we need to get also to calculate the PR. For instance, if the PR is 0.5, if we have 0.6 over here, this is 0.5, then the value of the Z0 is 0.1236. Okay, this is how to read it. Back to the example, we have the Z0, the TR 1.2, the PR is 0.6 something, 1.2, and this is 0.6. So we find this is 0.6 something in between here, and the TR is 0.12 or 0.2. The TR is 1.2. So 0.6 something here, and we find TR is 1.2 is over here. So the value is approximately here. You need to find out using interpolation. You have learned how to interpolate last week. Okay, so if it is in between, you calculate the delta with neighborhood data, and finally we get that Z0 is 0.865. Okay, 0.865. somewhere over here. 0.86 in between 0.83 and 0.87. Okay. The same thing, we need to find out Z1 from table D2. Okay. It was table D1. Now the next page is the table D2 in order to get the Z1. The same thing, the PR is 0.06, 0.6 something in this area, and then the TR is 1.2. 1.2 is in this area. So we get the Z1 around this 0.03, 0.04. To be exact, it is 0.038. Okay, this is how to get Z0 and Z1. After this, we use that Z0 and Z1 in order to calculate the Z, compressibility factor, after it is multiplied by the omega, 0.2. Then we get, this is the compressibility factor, 0.873. Remember that temperature was known, pressure was known, we need to calculate the volume. Okay, so you just put CRT over P, enter the values, you get the volume is 1481 approximately cubic centimeter per mole. Okay. Okay, up to this point, are there questions? Are there any questions? Which one easier? Depending. This one is easy actually. We just check in the table, then we find out Z. In the generalized system, it doesn't matter actually. We use normal butane, or we use ammonia, or we use methane, because we work with the TR-PR. So temperature is corrected after divided by the critical temperature. Pressure after it is divided by critical pressure. So it is valid for any gas actually, this TR and PR concept. Okay.